Hi, and welcome back to week 2. This week we are covering chapter 2 in your textbook, which is called Fundamental Building Blocks, Chemistry, Water, and pH. So in this chapter we will cover sections 2.1 through 2.7, and we have chemistry's building block, the atom, chemical bonding and the covalent bond, the ionic bond, the hydrogen bond, three-dimensional shapes and molecules, water and life, and acids and bases. Just as a heads up to this chapter is a lot of information to cover. It's essentially trying to cram an entire chemistry course into one chapter to give you some basic chemistry understanding so you can understand the topics that we need to cover in biology. So with that being said, it is a lot of information to go over. If you haven't had any chemistry before, this may all be new. So take breaks, repeat if necessary, go over sections at a time if you need to. Most chapters will not be quite this intensive with this huge amount of information crammed in, but this chapter does have a particularly large amount of information to cover. Before we start talking about these topics, let's go ahead and just get a definition of chemistry. So you understand when we say that we're talking about chemistry in this chapter, you probably have a basic idea from maybe high school of what chemistry is, but let's take this definition and then we'll break it down a little bit so we understand what it is. So chemistry, the definition, is the branch of science that deals with the identification of the substances of which matter is composed, the investigation of their properties and the ways in which they interact, combine, and change, and the use of these processes to form new substances. So now let's break down that definition so we understand what that's actually saying. So first up, let's look at chemistry being an investigation of the substances in which matter is composed and what that means. So essentially here we're looking at, when we look at the substances of which matter is composed, we're talking about the small building blocks that things are made of. These are things like atoms, elements, and molecules, and we'll talk more about these later. But essentially with chemistry, we're looking about what are the tiniest little pieces that things that we are studying are made of. Next part of the definition here, chemistry is the investigation of their properties. So when we talk about all these little pieces that things are made of, what are their properties? So what are these small building blocks like? So we talk about small building blocks that are in our body. Are they magnetic, acidic? Are they solids or gases? And these all have an important role in how they make up living things. Next up is the ways in which these things interact. So how do different types of elements and molecules interact within living things and within the environment? So how might these tiny little particles be necessary as nutrients or to get energy for our bodies or as building blocks to grow our own bodies? So different types of elements interact in different ways with each other and with our body to make our bodies and all living things function. And lastly, main other important part of this definition is how do these tiny little particles change? Water can be a solid, a liquid, or a gas depending on the temperature, and this state of water will impact life. So if water is a solid, that will significantly impact living things that can live in an area, water being in an ice state. Water needs to be in a liquid form in our body in order to function properly, but water can also exist in a gas if it gets hot enough, which could burn us. And so understanding how these little things in our bodies can change from one form to another is also important to understanding how they are important to living things. Next, let's look at why chemistry is important in biology. And everything in your body seems to know perfectly what to do. So you might have the thought that you want to move or run or eat, but when you do any of those actions, your brain is able to tell your body exactly what to do. And there's a lot of processes in your body that you aren't controlling, like your heart beating and your breathing, that your blood flowing through your body. All these things seem to work perfectly without you having to do anything at all. And your body knows when cells should grow and should stop growing. And if you eat food, your body knows whether it should use that food as energy or store it as fat. And the cells and everything in your body, they do what they do as a result of a chain of chemical reactions. So all of these different chemicals that we'll talk about in a little bit, how they interact and what reactions they go through will set off a chain of reactions in your body so that your body can function. In simple terms, if you take anything away, understanding how our body works and to understand how our body works and how all living things work, we need to understand the basic chemical components that make it up. So we need to understand what our body is made of or what other living things are made of in order to understand how they work. So next we'll dive a little bit deeper into chemistry and start talking about the things in chemistry that are important for us to know in biology. And the first thing that we're going to talk about is the atom. And the atom is the fundamental unit of matter. So if we break down anything that we look at and we break it down into its smallest piece that we can break it down into without undergoing a complex, like blasting it with something and shooting it apart, but the smallest piece that it naturally will exist in, we get to these things called atoms. And an atom is this picture shown on the right. And an atom is something that has at its core, or what they call the nucleus, it has things called protons and neutrons. And essentially what these are is these are very, very small particles. Neutrons are neutral, they have no charge, and protons are positive, they have a positive charge. And then circling around our nucleus are these rings of electrons, which have a negative charge. This is an example of a helium atom. We'll talk more about how the number of protons, neutrons, and electrons determines what type of atom you have in just a little bit. Let's look at the structure of an atom in a little bit more detail. First off, as I mentioned, the term nucleus, or the center of the atom, this is this area here, and we tend to have these particles in the center that are very densely packed together, and the particles that are in the center are these little P's, which stand for protons, and protons have a charge of +1, or you can just say they're positive, but they are equally positive to electrons, which we'll talk about in a second, that have a charge of -1. But anyways, protons are positively charged. They're in the center of the nucleus, and they have a weight of what we call 1 atomic mass unit. You can just think of them as a weight of 1. Neutrons are also in the center, these yellow ends, and neutrons have a charge of 0, so they don't have any charge, negative or positive, but they do have a weight, just like protons, of 1 AMU, a weight of 1. Around all atoms, we have these electrons floating around here, and these electron rings or electron shell, essentially just the outer layer of these atoms, are the electrons floating around. And the electrons have a charge of -1. You can also just say they're negative. And they have a weight of almost 0. So nothing can weigh exactly 0, but the weight is so small that it really doesn't interfere with the properties of any particular atom that you're talking about. Let's just go over in a table form here, just to review. So you have these different types of particles. They call them subatomic particles because they're sub meaning part of, atomic, and atom. So these particles that are part of or within an atom. You have protons, neutrons, and electrons are the 3 types of particles. Protons and neutrons are located in the nucleus. Electrons are located in the outer shell. Protons have a weight of 1, neutrons a weight of 1, electrons a weight of 0, protons a positive charge, neutrons no charge, and electrons a negative charge. And each of these properties, how much it weighs and what its charge is, tell us, basically determine what type of atom it will be and how it will interact with other atoms. And so we'll go into that next. So first off, the number of protons in an atom will determine what kind of atom it will be. So you can change the number of electrons, the number of neutrons, and it will change the properties a little bit, but the number of protons is what determines what kind of atom it will be. And we call a type of atom an element. Examples of elements include things like hydrogen, carbon, and oxygen. And each of these elements has a different number of protons. So an atom is just a one of those small particles made up of protons, neutrons, and electrons. And if a substance is made up entirely of one type of atom, so if you have, let's say, a group of helium atoms, we call that an element. An element just means that it's all one type of atom. So for example, all helium or all oxygen. So an atom is the name of the general particle. So we could call this any of these small pieces would be called an atom. But an element is when we give it a name. For example, we name it helium. That's the name of the element. We name this oxygen. That's the name of the element. So let's look next at the periodic table and how we know what type of atom it is. So this picture on the right here shows what we call the periodic table. It gives a list of all the different types of elements that we know about. And also from this table, we can determine a lot of information about the specific element that we're looking at. And the main thing that we are going to be concerned with for this course is knowing, so again, the periodic table shows all of the different types of atoms, which are called elements. And the main thing we'll be concerned with is the number of protons in that atom. And that gives us the name of the element. So let's start with number 1 on the periodic table. Number 1, you can see this tiny little 1 right here. So we're not looking at this one here. That's telling us the column number. So we don't want to look at that one. We want to look at the tiny little number here inside the box with the element. And this tiny little number 1 here has a letter H on it. Because it has 1 here, that means it has 1 proton. And anything with 1 proton in it has certain properties, and we call that element hydrogen. So this abbreviation here, H, stands for hydrogen. And so every element is given an abbreviation to make it easier to work with. And again, this number here, they call this the atomic number, and it's just the number of protons within that atom. And again, the number of protons gives us the name of the element. For number 1, it's hydrogen. Let's move on now to number 2. We have to jump across the periodic table over here. And again, this number in this tiny little number in the upper left-hand corner is again the number of protons. So we have 2 protons in this element. And the name of the element is helium. It's abbreviated He, and He stands for helium. Moving on next to number 3 in the periodic table. You might be able to guess by now that periodic table number, element number 3 here has 3 protons. This element is lithium, and it is abbreviated Li. And so every atom or element on this periodic table has this number in the upper left-hand corner, and that is the number of protons in that element. And the number of protons determines what type of element it will be. 4 protons is beryllium, 5 protons is boron, 6 protons is carbon, 7 protons is nitrogen, etc. And just to remind you of what this term is, atomic number is just this number that you see here in the upper left-hand corner, and that is the number of protons in the element. Let's look at a picture of what I'll call for now normal elements. These are elements in their most common state. And we talked about the number, if this was a box from the periodic table, this number in the upper left-hand corner is called the atomic number. It's the number of protons or positively charged particles in the atom. So here we have got an atomic number of 2. This is helium. So in general, if you have 2 protons or 2 positively charged particles, you are typically going to also have 2 neutrons, neutral or no charge particles, and 2 electrons, 2 negatively charged particles. So atomic number is 2, that would mean your number of protons, neutrons, and electrons are also 2. So if we look at lithium, it has an atomic number of 3 protons, 3 neutrons, and 3 electrons. This is the most common form of the atoms that you will find. If you were to change the number of protons, you would turn it into a different element. So if we change the number of protons from 2 to 3, it goes from hydrogen to lithium. If you were able to add a proton to this, it would changing the number of protons completely changes the element to a different type of element, a different name. You can change the number of neutrons or electrons, and you will still be in this. As long as you keep 2 protons, you could change the number of neutrons or electrons, and you will still have helium, but you will have a different form of helium. So in the next couple of slides, we're going to talk about what happens when you change the number of neutrons and the number of electrons in an element. First, let's look at what happens when you change the number of neutrons in an element. And when you change the number of neutrons, we call this an isotope. So here's our normal helium. Our normal helium, once again, has an atomic number here of 2, which would mean that it has 2 protons, 2 neutrons, and 2 electrons in its most common state. So 2 protons, 2 neutrons, and 2 electrons. Now here in an isotope of helium, what we call helium-3, you'll notice that the atomic number is still 2. We can't change the atomic number because that would change it to something other than helium. So atomic number is still 2, so the number of protons is still 2. The only thing that changes in an isotope is the number of neutrons. So in helium-3, we have 1 neutron. So that's the only known isotope of helium, is one with 1 less neutron, so 2 protons, 1 neutron, and still, just like before in the normal helium, it has 2 electrons. And the way that they get the name of the isotope is by counting the number of protons and neutrons, so the number of particles in the nucleus here. So it has 1, 2, 3, so they call it helium-3. The normal state here has 1, 2, 3, 4 protons and neutrons, so you could call it helium-4. Also, it is normally just called helium because just being called helium indicates it's in its normal state, and we would expect it to have the 2 protons, 2 neutrons, and 2 electrons. So you don't normally need to say helium-4 for the normal state. You could, it would mean the same thing, but for the isotope, to know what kind of isotope it is, you would need to say helium-3 to indicate that it's an isotope and that it has a different number of neutrons. So just as a refresher here, in an isotope, your number of protons stays the same, your number of electrons stays the same. The only thing that changes is the number of neutrons. So knowing what an isotope is, that it's an atom with a different number of neutrons than a typical atom. And that being an isotope doesn't sound that exciting, but it turns out that isotopes have a very practical use. And one isotope that we commonly use is an isotope of carbon. So living organisms take in carbon constantly from the food they eat, and most of this carbon is carbon-12. There's a small amount of carbon-14 in the air. Carbon-14 is an isotope of carbon-12 because it has a different number of neutrons. And so living things take in a small amount of carbon-14 into their bodies. And carbon-14 breaks down or decays into nitrogen at a very steady rate. So it will lose a proton and become nitrogen. And this happens at a consistent rate. So as it sits in the ground and the living organism's body sits there, the longer it sits there, the more this carbon-14 that was initially present will break down and be gone. So essentially every 5,730 years, half of the carbon-14 that was present in that living organism will be gone. So you'll have 50% of the original amount of carbon-14. After another 5,730 years, or a total of 11,460 years, another half of the carbon that was present here will be gone. So at this marks 5,730 years, there was 50% of the carbon, of the original amount of carbon. Now in another 5,000 plus years, half of this 50% will be gone. Half of 50% is 25%. So at 11,460 years from the death of that organism, there will be 25% of the carbon-14 left. The amount of time that it takes something to break down from the original amount to have half of it left is called the half-life. And so the half-life of carbon-14 is 5,730 years. And every 5,730 years that you go from the death of the organism, it will continue to reduce by half the amount that was there before. So scientists can use the amount of this carbon-14 isotope present to date something, and we call this carbon dating. So carbon dating is essentially looking at the amount of carbon-14 isotope present and using that amount present to tell how long ago something died. And by telling how long ago something died, we can see when it lived. And you'll read more about this topic in your essay reading on pages 26 and 27 of chapter 2, and that will be the topic of your week 3 discussion. So next week, if you're watching this lecture during week 2, next week in week 3, you will discuss carbon dating in your week 3 discussion. Next, let's look at what happens when we leave the number of protons and neutrons the same, but we change the number of electrons. When you change the number of electrons, they call this an ion. So we had isotope is when you change the number of neutrons. Ion is when you change the number of electrons. And what happens when we change the number of electrons is in a normal atom, we have, let's look at carbon atom first. So carbon has an atomic number of 6, which would mean in its normal state, it has atomic number of 6, has 6 protons, 6 neutrons, and 6 electrons. Now the number of protons or positive charges is 6, and the number of electrons or negative charges is 6. So if we have 6 positives and 6 negatives, the charges cancel each other out and our overall charge is 0. Now in an ion, we have a different number of protons and electrons. So common carbon ion that you might see is carbon C4 negative. And what this means is that there's still an atomic number of 6, so we can't change that, which means the number of protons is still 6, the number of neutrons is still 6. But in this particular ion, there are 10 electrons. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons. And so what happens here is, let's look at our number of protons as 6. That means we have 6 positive charges. Our number of electrons is 10. That means we have 10 negative charges. And so if you put these charges together, you have positive 6 minus 10 for the negative 10 electrons here, and the positive 6 protons. So if you remember from algebra, when you add two numbers together, and one's a positive and one's a negative, you take the charge of the larger number. So 10 minus 6 is 4, and we end up with a negative charge. So you're starting with 6 and going backwards 10 spaces. So when you have positive 6 and negative 10, that leaves you with a leftover charge of a negative 4. And the way that we write an ion is we write C for carbon, and then we put the charge right up here next to it, so 4 minus. So just by writing C 4 minus, you know you have this carbon ion with a charge of negative 4, which means you have 4 more electrons, 4 more negatives than you do protons or positives. Now it turns out that electrons have an important role in determining what different atoms of what kinds of elements will want to combine together. So again, electrons carry a negative charge, and electrons will combine with other elements, or elements will combine with other elements based on the number of electrons that are present. So we'll go over that in the next slide, why this is. Let's look at how electrons are organized around the atom now. So you've seen in the pictures that we've shown before, there's these rings around on the outer edge, call them rings or shells, where the electrons are located. Now hydrogen has 1 proton and 1 electron, atomic number of 1, and in this first ring around an atom, this first ring can hold up to 2 electrons. That's always the case no matter what element you're looking at, that there can be up to 2 electrons. Now hydrogen just has 1 electron, And what an atom would like to have to be the most stable is 2 electrons in this first ring. So hydrogen only has 1 electron, so it's not very stable and it's very reactive. That means it will like to combine readily with other atoms. Now helium, on the other hand, has an atomic number of 2 protons, and 2 electrons. So this outer ring with 2 electrons is full. It has its 2 electrons, it's very stable, so it does not tend to combine with other atoms very readily. Now, that's the first ring here around the atom. If we have more than 2 electrons in an atom, so typically in an element with an atomic number greater than 2, so 3 or larger, you will have, let's look at carbon next, you'll have 2 electrons in this first ring, and then however many more electrons you need to have, you can have up to 8 in this second ring. So carbon has an atomic number of 6, so 6 electrons, and 2 electrons can go in the first ring. So we've used up 2, so that means we have 4 more electrons, and 4 of these electrons will be in the next ring. Now this ring can hold up to 8 electrons. So each ring outside of the first ring can hold 8 electrons. Now carbon would really like to have 8 electrons in its outer ring. It only has 4, so it's not very stable, and it will readily react with other atoms to try to fill up that outer ring. Let's look over here at neon. Neon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. We have 2, atomic number of 10, 2 electrons in the first ring, 8 electrons in the outer ring. Now, since its outer ring is full with 8 electrons, it's very stable. It does not readily react with other atoms. So as you keep going up the periodic table and your atomic number gets larger and larger and your number of electrons gets larger and larger, you can keep adding more rings. So sodium has 1, 2, 3 rings, and every ring except for that first one can hold 8 electrons. So the second, third, fourth, fifth, sixth, however many rings you need, can each hold up to 8 electrons. And when we talk about how stable an electron is, and when we're looking at what an electron will combine with, we're typically only looking at this outer ring of the electron. And that's the most important information on electrons that we need to see, is this outer ring full. So whether the first ring is the outer ring or the third ring is the outer ring, we're looking to see, is that outer ring full? Now, if the outer ring is not full, atoms can do 2 things. So they can either share an electron with another atom, so that each of the atom's outer rings are full. If they share an electron, then they become bonded together, and their bond is called a covalent bond. We'll go over that more next. Just want to give a brief overview here. If atoms give or take an electron, so for example, if this sodium here with 1 outer electron gives it away to another atom, it would be happy now because its outer ring is full. This would become the new outer ring, and the other atom would take this electron away. So when 2 atoms become bonded together based on giving or taking electrons, then their bond is called an ionic bond, and I'll go over both covalent and ionic bonds later. So just to review the main takeaway from this slide, the first outer ring can hold 2 electrons. Each outer ring after that can hold 8 electrons. And elements are most happy, most stable, when their outer ring of electrons is full, whether that's 2 electrons or 8 electrons. Let's look at an example of covalent bonding. So hydrogen, if we look at it on the periodic table, has an atomic number of 1. That means it has 1 outer electron. So this hydrogen has 1 outer electron floating around it, and this green colored hydrogen also has 1 electron floating around it. Now the 2 hydrogens, when they get close together, they can share these 2 outer electrons, and so each of these electrons will then equally go between the 2 hydrogens. So the green and the blue electrons will both go around this blue hydrogen, and the green and blue electrons will also both go around the green hydrogens. So each hydrogen now has access to 2 outer electrons, 2 electrons in their outer ring. They are both full, they are both stable. And so that's a common combination that you see because they are both, when they get close to each other, they share those electrons, they become bonded together in a covalent bond and become more stable. Let's look at another example. Hydrogen, as we just mentioned, has 1 outer electron and would like 2. Oxygen is atomic number 8 on the periodic table. It has 2 oxygens in the first ring, 6 oxygens in the outer ring. It would like 6 electrons and 2 electrons in the first ring, 6 electrons in the outer ring. It would like 8 electrons in the outer ring. So hydrogen and oxygen are both not very stable on their own. So here we have a picture. We have our hydrogen with 1 outer electron, our oxygen, the total again of 8 electrons. So 2 can fit in the first ring. The remainder, which is 6 more, go in the outer ring, and it would like 8 in this outer ring. So when you get 2 hydrogens that come close to an oxygen, they can share all of their electrons. So those electrons, the 2 electrons from the 1 electron from this hydrogen, the 1 electron from this hydrogen can both get shared. That gives this oxygen access to 8 electrons in its outer ring. And then oxygen can also share one of its electrons with hydrogen. So hydrogen has access to 2 electrons in its outer ring here, and then this other hydrogen can also share an electron with oxygen. And so hydrogen also then has access to 2 electrons in its outer ring. So both of the hydrogens and the oxygen all have access to full outer rings. And all of these atoms, both the hydrogen and the oxygen atoms, are happy, or they are full, they are stable. And so this is a very common combination you see, which is H2O. H2 stands for 2 hydrogens, and O stands for the oxygen, which you may know as water. So we just looked at hydrogen and oxygen sharing electrons in their outer shell to form what we call a covalent bond, where they share those outer electrons. So each atom has access, the hydrogen and the oxygen, as we mentioned, to a full outer ring of electrons. Now, what happens in reality in this particular case with water is oxygen has a lot more electrons here. And so because it has a lot more electrons, it has a lot stronger pull for these shared electrons. So when it gets next to hydrogen, it basically tends to hog these outer electrons. You could think of it as sort of the more greedy atom for these electrons, and it hogs them and holds on to them more of the time than the hydrogen atoms do. And so what happens is the electrons spend more time circling around oxygen than they do circling around hydrogen. They still will go back and forth between both, so both will still have access to that full outer ring. It's just oxygen has those electrons more of the time. Now, if you remember, electrons are negatively charged. And so what happens is, since oxygen has the electrons more of the time, the oxygen end of this water molecule, or this combined hydrogens and oxygens, the oxygen end will end up with a little bit more of a negative charge on this side of the molecule. So it'd be like thinking of a magnet, and you have a positive and negative side of a magnet. Well, oxygen would be like the negative side of that magnet. It's negative more of its overall negative charge more of the time. On the other hand, the hydrogens, since they lose their electrons more of the time, they end up with a slightly positive charge on this end of the molecule. Now, when a molecule ends up sort of positive on one side and negative on the other, we call this a covalent polar bond. And polar just means, you think of it like poles. Polar means that one end is negative and one end is positive. So the electrons are still shared, so all the atoms do have access to a full outer shell, but one atom in a covalent polar bond will have the electrons more of the time. Now let's look at what happens when the atoms are arranged symmetrically around each other. So in the last example with hydrogen and oxygen, the 2 hydrogens tend to sit toward one end, the oxygen towards the other end, and so you have that pull in one direction. In this example here, we have methane. Methane has 1 carbon and 4 hydrogens that share their electrons to get full outer shells. And the hydrogens, as you can see, are all arranged around the outside symmetrically. So the hydrogens all have a little bit positive pull around the outside. The carbon has a negative pull toward the inside, and they all cancel each other out because of this symmetrical arrangement. And so when something is symmetrically arranged, the charges cancel each other out. There's no positive or negative pull in any one direction. And this would be an example of a covalent nonpolar bond. So nonpolar meaning that the charge, there's no pull of positive and negative in any certain direction. Sort of all the charges within that molecule cancel each other out. So we've been talking about covalent bonding when electrons are shared. Now there are circumstances when instead of sharing electrons, an atom would be happier just to give up an electron or to take the electron for itself and not to share it. So remember an ion, the term ion means an atom with a charge. So it's given up or accepted electrons. So it has a different number of electrons. Now when an atom is happy to give up or accept electrons and become an ion, it can form a type of bond called an ionic bond because it would like to be an ion. So if we look at sodium and chlorine here, sodium has an atomic number of 11, chlorine an atomic number of 17. So if we were to draw out 2 electrons in the first ring, sodium would have 8 electrons in the second ring, and then 1 extra electron left in the third ring. Now chlorine has, with 17 electrons, has 2 in the first ring, 8 in the second ring, and 7 in this outer ring. Now chlorine with 7 in the outer ring has a really strong tendency to want to take one more to keep it to itself and have a full outer ring. Sodium has a really weak charge because there's only 1 electron in this outer ring, and it is really happy to just give away that extra electron, and then it's full and happy and stable with a full outer ring here. So each of these atoms, sodium and chlorine, are happy to work together. Sodium to give up an electron, chlorine to accept an electron, to each get a full outer ring. So they like to come together to do that exchange of electrons, and the bond that they form when they come together is called an ionic bond because now sodium has become positive from giving up that electron. So it gave up a negative, so it becomes more positive. Chlorine accepted a negative, so it becomes more negative. So each of these is now an ion, and they formed an ionic bond. You've probably heard of this particular combination, sodium and chloride. Sodium chloride is just table salt. So the common salt that you eat every day is a mixture of sodium and chlorine put together, and we get table salt, an ionic bond. So we talked about what can happen when a covalent bond is when atoms share electrons, an ionic bond when atoms give up or accept an electron to form a bond. There's one last type of bond that doesn't involve sharing or giving or taking, but instead is based on a positive negative charge attraction. So we talked about hydrogen and oxygen go together to form water, and that this is a polar covalent bond, meaning a bond with shared electrons. So here's our 2 hydrogens and oxygens, but they end up with sort of a positive charge by the hydrogens and a negative charge by the oxygens. Now what happens is one water molecule has a little bit of an attraction to the other end of another water molecule. So the positive end has a little bit of an attraction to the negative end, just like 2 ends of a magnet would be attracted together. And this attraction can occur on any of these different ends where there's a positive and a negative. And so what happens here is you get water molecules that are attracted to each other with a very weak bond. It's not a strong bond, but they are attracted to each other with a weak bond. We call this attraction a hydrogen bond. So it's weaker than the covalent or ionic bond, but it is a bond that can exist. It's very easy to break. You can see an example of this bond. If you put a drop of water on the table, the drop of water stays in a ball. It doesn't just spread out flat like, say, if you poured a drop of oil on the table. And the reason that that drop of water stays in a ball is because it's all attracted to itself. So it's sort of forming this sphere shape. It doesn't want to spread out onto the rest of your table. It wants to stay in that ball because all of these water molecules are all attracted to each other. But as you can notice, it's very easy to take your finger and separate the water from itself. It's not a really strong attraction, but there is that attraction there. Again, this is called a hydrogen bond. We're going to skip section 2.5 in our lecture. You can also skip it in your textbook if you would like to. Now, water, as you know, is really important to life as we know it, and there are a few reasons for this. So let's go over some unusual properties of water that make water important and essential for most organisms on Earth. So first of all, water is a great solvent. It's great at breaking down substances such as salt. So if you take salt and put it in a jar of water, the salt will dissolve in the water. It looks like it disappeared, but it's actually just dissolved. And water is really great at breaking down a lot of different things. Second, unusual property of water is that ice floats. You probably wouldn't have thought much about this before, but this is actually really important to life on Earth. So when water is a liquid, the hydrogen bonds are constantly being pulled apart and broken, and so water is moving very rapidly and the water is fairly dense. When water starts to become frozen, the hydrogen bonds become maximized and stuck in place. And so this causes the water molecules to be further apart from each other, causing it to be less dense, and this less dense ice being less dense than water, causes it to float on water. And this is really helpful to living things because the ice on top of oceans and ponds, as the air gets colder and that top layer in areas where the water freezes, that water begins to freeze on the surface, the ice floats, and only the surface of a lot of ponds, rivers, lakes, and oceans will freeze. And it keeps the water underneath a livable temperature and a liquid so that living things can live in them. If ice were to sink, on the other hand, if water when it froze became denser or stayed the same density and ice could sink, then ponds, lakes, and possibly parts of the ocean would just become a solid block of ice and no water-dwelling organisms would be able to survive there. So hydrogen bonds, again, cause ice to float, super important to life on in the water. Third, water has a high specific heat. So what does this mean? Specific heat is the amount of energy it takes to change something from a solid to a liquid or a liquid to a gas. And it turns out it takes a lot of energy to change water from one phase to another. So what this means for us is that water is a great insulator. It's hard to change it. The temperature around water very much. So this explains why in coastal areas we don't have extreme changes in temperature between the seasons. And water being a great insulator is also important for lots of other reasons, but that's a good example is when you go to the coast, the water keeps the temperature there more constant. It's also helpful for keeping the temperature constant in your own body. And our last unusual property of water that we're going to cover is that water has cohesion and surface tension. So again, we had talked about earlier that when you drop a drop of water on the table, it will stick together due to that hydrogen bonding. This is called cohesion. And cohesion makes the surface of water, it causes all those surface water molecules to stick together. And they don't want to stick to the air above them, so they tend to stick very closely to each other on the surface and to that water below them. And this creates sort of a barrier on top of the water. We call that surface tension. And that surface tension allows some organisms to walk on water. So you can see the basilisk lizard down here is able to run on water. These water striders can float and walk on top of the water. Here are some western grebes doing something they call rushing in Upper Klamath Lake. And that's a mating practice that they do where they run on the water and move back and forth. So lots of different organisms are able to use that surface temperature and either live on or run on the surface of the water. So finally, we are on to our last topic of chapter 2, and for section 2.7, we are going to talk about acids and bases, which are measured with something called pH. So pH is a measure of how acidic or basic something is, and pH ranges from 0, which is the most acidic, and over here on the right we have the pH scale. pH of 0 is the most acidic something could be, all the way down to, so all of this is acidic, pH 0, 1, 2, 3, 4, 5, and 6. When we get to pH 7, that's what we call neutral. It's neither acidic nor basic, like pure water. And then as we go above 7, 7 to 14, pH of 7 to 14 means something is basic. And the The higher the number, the more basic something is. The lower the number, the more acidic something is. So again, 0 to 7, 0 to less than 7 is an acid, pH of 7 is neutral, and greater than 7 to 14 is a base. Acids tend to be have the properties that they are sour, corrosive, and they will burn your skin. The more acidic they are, the more they could burn your skin. So you would not want to test to see if something's an acid by tasting it to see if it's sour, but most acids do in fact taste sour. One acid that you can taste that's actually very acidic is lemon juice. Has the same acidity, if you can see in the picture, it's pretty small font, but as gastric stomach juice. The stuff inside your stomach that is breaking down your food is the same acidity as lemon juice. One reason why it's not a really good idea to suck on lemons, because acids are corrosive, and they are also corrosive on your teeth. So some other examples of acids are vinegar, lemon juice, coffee, tomatoes. Soda is also very acidic. Here at the most acidic end, we have battery acid, still pretty acidic, is your lemon juice and your stomach acid. Then we have soda, still pretty acidic. Tomatoes getting less acidic, and black coffee less acidic, and then urine, not very acidic, but just a tiny bit acidic. Moving on to our bases. Bases tend to be slippery to the touch. So if you have ever used a cleaning product with some bleach and noticed that your fingers felt very slippery after you touched it, that's the bleach feeling they give. They have a very slippery feeling to them. They tend to taste bitter, and like acids, they will also burn the skin. And the more basic they are, the more they will burn your skin. Some examples are lye, which is what they use to make soap, bleach, baking soda, and ammonia. And as you can see here in the picture, blood is very, very slightly basic, just a tiny bit. Baking soda is a little bit more basic. We have ammonia getting pretty strongly basic here. Bleach, very strongly basic, and super, super basic is lye. Now the technical definition that your book uses, just so you know that definition, is an acid tends to yield hydrogen ions in water. So if you were to put an acid into water, they say an aqueous solution, this means a water solution, then it will give off hydrogen ions or individual hydrogen atoms. Bases, their technical definition is that if you were to put a base into water, it will accept hydrogen ions. So it will take hydrogen ions in. So that is the technical definition between what makes something acidic or basic. But for our purposes for this course, make sure you know the pH of an acid and some examples of acids, and the pH of a base and some examples of bases, and also their characteristics, such as sour, bitter, etc. All right, so that was a lot of information to cover in one chapter, but we are finally at the end of chapter 2. And I will be in touch with you next week. If you have any questions as you go about this week, please don't hesitate to ask them.